biologically, river flow tends to be so from a physical point of view, from the point of view of the hydrologist, what happens here is that at the beginning you have a catchment that is empty. The tank is empty. So it starts raining, but you don't get much flow, because you get some flow, of course, but not much flow, because the catchment is empty. Then, given that rainfall is higher than the flow, so the inflow into the tank, which is rainfall, is higher than the outflow from the tank, which is Q, and it's higher because it's raining, and at the beginning you don't have any river flow. So given that rainfall is higher, it means that your tank catchment is accumulating storage. So the storage is increasing. And therefore, for increasing storage, you have increasing river flow. But still, rainfall is higher. So the storage is steadily increasing, though at a decreasing rate. So the storage at the beginning increases very quickly and then increases slower. And then you get to a level of storage such that rainfall is almost at the same value of outflow. And therefore storage doesn't accumulate anymore, or the accumulation is very, very slow, and therefore the asymptotic tendency, which is fine. I mean, if you think at a real catchment, it is reasonable that if it rains over the dry catchment, you start increasing storage, but you don't see any river flow at the beginning. And then, when storage increases, you have the river flow increasing. And we all know that when a catchment is saturated, meaning that the storage is at its upper level, you get to a situation where river flow is equal to rainfall. And this is a very dangerous situation. Usually you get a flood when you have this situation. Why is that? Because typically it's originated by very heavy rain, because in order to get to saturation you have to get a very long and heavy rain, and then when the storage is depleted, the catchment doesn't have any more possibility to attenuate rainfall. Storage is a mitigation effect, it's an attenuation. It's also called lamination of rainfall. And when the catchment is saturated, there is no more possibility for the catchment to mitigate rainfall. And therefore, the model is reasonable, and the graph should be, no, it's not depicted. I may add this graph, but anyway, it's simple. So this is the moral of the story for the linear reservoir, and you may notice that to perform the simulation, we need one specification, not only rainfall, not only the geometry of the catchment in order to compute the volume of rainfall, we need to specify K. And what does it mean, K? K means that if K is very long, I say long because it's a time, remember it's a time. So if the value of K is high, which means that K is long, remember the original relationship from which we started, the energy balance. The energy balance was Q is equal to WT, QT is equal to WT divided by K. We wrote it in a different way at the beginning. We wrote it in the form WT is equal to K times Q, but it's the same story. So what happens if you have a large K value? What happens if K is long? You see that you get a decrease of river flow. which means that the attenuation effect I mentioned before is more significant. On the other hand, it means that storage attains a higher value. So increasing K means that the catchment is capable of storing water, and means that the river flow is then decreased. This is a situation that we may like, because it means that the catchment has two behaviors. First, the behavior to mitigate extreme rainfall, and therefore, by mitigating extreme rainfall, the risk of flood is decreased. But there is a second effect. The high storage, given that we are interested in using water resources, we like the situation where catchments have a lot of storage. We like the situation in which catchments can retain water. So they work like a dam. What is a dam? Is an impound of reservoir, accumulation of volume of water when it rains a lot in order to use it during the dry season. If the catchment has a lot of storage, it does the same. It takes a lot of water during the rainy season, keeps it, and delivers it in the form of river flow during the dry season. It's interesting if you try to set up a very simple linear reservoir model and you run simulations. It's very interesting to see the effect that you obtain if you increase K. Maybe that we have time to see this. What you obtain is a prolongation of the hydrograph. So a lot of water released during the drought season. But of course, we cannot play with K. We cannot impose our value. We need to use a K value that reflects the behavior of the catchment. K is what is called a parameter, meaning a coefficient into the model equation that doesn't change the shape of the equation itself. It's a linear equation, so it's a linear model. Doesn't change. If I change the value of K, I cannot change the behavior of the model, but it changes the specific behavior of the model. Like I obtain a model with a high storage instead of a model with a low storage. So it's a coefficient into the equation that doesn't change the structure of the equation, but changes its shape. This is the definition we adopt for parameter. So a coefficient into the equation that doesn't change the structure of the equation, but changes its shape, specific shape. It's written somewhere here. And how it is estimated then? It is estimated usually, and then we make the break, by matching observed versus simulated flows. And we will dedicate some time to this parameter estimation procedure in a subsequent lecture. So again, K is a parameter, and it's usually estimated through comparison between observed and simulated river flows. Okay, we can make a break now, 15-minute break.